Today we're going to finish up lesson 4.2, the B part of that lesson. So I've been saving this. I wanted to tackle it at the end, and it just is a good lesson for you guys to watch on a Monday to get ready for the week. So we're going to talk about the mean value theorem. So we've had some theorems over the course of our semester so far. Today we're going to talk about the mean value theorem, which specifically requires the derivative. So the mean value theorem requires not only continuity, but it requires differentiability as well. So we had some other theorems before. We had the intermediate value theorem, and it required continuity. That was its only requirement. We had the extreme value theorem. That required continuity and a closed interval. Now we have the mean value theorem, which also requires continuity on a closed interval, but it adds another layer. And so if it's continuous on the closed interval, and if it's differentiable at any point. Okay, so those are the setups. Those requirements have to be true for the mean value theorem. All right, so then, what is the then? Then there is at least one point at C, okay, at which the instantaneous rate of change equals the mean rate of change. Okay, so let's diagnose that. What does the instantaneous rate of change mean? All right, well, we've defined instantaneous rate of change as f prime. Where is this happening? It's happening at C. All right, so the instantaneous rate of change. Then we're told that it equals something. Well, what does it equal? It equals the mean rate of change. Now, the word mean doesn't mean angry. It means average. And so if this is supposed to equal the average rate of change, well, we know the formula for the average rate of change is f of something minus f of something else over the interval of subtraction. So what points do we use? Well, that's where the closed interval comes into play. And it'll be b, f of b minus f of a over b minus a. So this is what the mean value theorem says, that the instantaneous rate of change is equal at some point to the average rate of change, or the mean rate of change, that these two things are equal to each other at least once on a closed interval. So what does that mean visually? Well, a secant line represents the average rate of change, the slope. Okay, or instead of the word average, we use the word mean. So the slope here is equal to the mean, I'm going to run out of room, the mean rate of change, which is another word for average. Okay, that's the secant slope. Well, that means at least once there is a point on the closed and differentiable interval where there's one point, and its slope is the instantaneous rate of change. And so visually it means we have parallel lines. If the interval is continuous and differentiable on a closed interval, if the function, is continuous and differentiable on a closed interval, then at least once the mean rate of change and the instantaneous rate of change are equal to each other. So that's where we get f prime of C equals f of b minus f of a over b minus a. That is the mean value theorem. Okay, here's another drawing of it. Okay, here's your point C. and there is a tangent line, an instantaneous rate of change. Well, can you find a closed interval whose mean rate of change or average rate of change is the same? So we can kind of eyeball it. And it looks like maybe here would be a closed interval whose mean rate of change or average is approximately equal, should be exactly equal, or parallel. There could be multiple. You could find another closed interval connecting two lower points and still have a parallel line. I could find slightly higher points and connect them and have a parallel line. Okay, we're saying that this happens at least once. That last drawing was very poor. Move it down a little bit. Okay, that happens at least once, if not multiple times, on the tangent line. Okay, all right, so let's do an actual example of it. So show that the parabola f of x equals x squared satisfies the hypothesis, and then find the solution. Okay, well, it's a parabola. F of x equals x squared is continuous, and it's differentiable by definition on the interval 0 to 2. Okay, so since that's true, then we can move forward. So we need to find the point C that would be equal to f of 2 minus f of 0 over 2 minus 0. So f prime at C would be 2c. That's the derivative with c plugged in. Okay, the derivative is 2x, but we're finding it at point C. F of 2 is 4, minus f of 0 is 0, over 2 minus 0. So that gives me 2c equals 2, so c is 1. Okay, that matches up here with c to be 1. And so c does have a parallel instantaneous rate of change when you compare it to the average or mean rate of change. So it happened once on this interval. Other functions might have it happen more than once, but it's guaranteed to happen at least once. If f of x equals the square root of x squared satisfies the hypothesis of the mean value theorem, then find the value of c that results from the mean value theorem. All right, you might want to grab your calculator out right now and take a look at this graph. If you pause the recording a minute and take a look at the graph, you might be surprised at what you see. You might expect this function to look one way, because the square root of x squared plus 1, well, the square root and the square cancel each other out, and so that would be x plus 1. So wouldn't we expect that to look like a line going through the y-axis at 1 with a slope of 1? Isn't that what we would expect? But when you graph it, you discover it's an absolute value. So why is that? It's because this is not exactly true. If you have the square on the outside of a square root, then the answer to that is x. But if you have a square on the inside of the square root, the definition of that is the absolute value of x, because the square happens first, and it might wipe out any negatives that we would have, and then the square root would be a positive number. And so in this case, because of the positioning of the square root, there is an absolute value here. So this graph turns out to be an absolute value, which means it has a corner, which means it's not differentiable, which means the mean value theorem does not apply here. So the MVT doesn't apply because f of x is not differentiable on the interval. So be careful that you've considered not only the continuity, but the differentiability. Okay, if f of x is this cubic function, if that satisfies the hypotheses of the mean value theorem, then find the value of c. All right, this is a cubic, and the cubic doesn't have any funny business going on. We know what a cubic looks like. A cubic is continuous and differentiable. So we would just clearly state, since f of x is continuous and differentiable on -2 to 2 because of the definition of a cubic, then the mean value theorem applies. All right, now we're ready to do the mean value theorem. So f prime of c is going to be f of 2 minus f of -2 over the interval 2 minus -2. So f prime of c would be 3x squared, except we want to plug c into that, so it'll be 3c squared minus 4. And then f of 2, when you plug 2 in, you're going to get 2 cubed minus 4 times 2, you actually get 0. When you plug in -2, you get -8 minus 4 times -2, which is 0 again. So we have 3 squared minus 4 is equal to 0. So c squared must be equal to the fraction 4/3, which means c is plus or minus the square root of the fraction 4/3, which is better written as 2 over rad 3 plus or minus. So if we were to draw this, we would find out that the 2 and -2 have an average slope, or a secant slope, of 0. That means it's horizontal connecting those two. We would also find out that at 2 over rad 3 and -2 over rad 3, they also have horizontal. So we've got to picture this a minute. Okay, we've got 2 here. We have -2. That's on the x-axis. So this parallel line connecting those two has a horizontal slope, an average rate of change of 0. And then at 2 over rad 3 and -2 over rad 3, we also have an instantaneous rate of change that is the same as the mean rate of change. This can be applied to a real-life situation as well. So let's assume a car begins and ends at rest. Over an 8-second time interval, the car is able to travel 352 meters. What does the mean value theorem guarantee about this situation, and what does the intermediate value guarantee about this situation? All right, so this car is both continuous and differentiable. How do we know that? Well, because we live in reality. Okay, we know that this car is not going to apparate, if you're a Harry Potter fan, from one place to the other. It is going to go in a continuous motion. It's not going to disappear and reappear. This is continuous. And so we're not going to have any sudden changes. So this is, the mean value theorem is guaranteed. So is the IVT is guaranteed. All right, the mean value theorem, what does it guarantee? Okay. Well, the mean value theorem guarantees an f prime of c must equal f of b minus f of a over b minus a. F of b is the end, that's 352, minus the beginning, which is 0 because it ends and begins at rest, and then 8 minus 0. So then we end up with 352 divided by 8. So we have 44. So the mean value theorem guarantees that the average rate of change is 44. So since The average rate of change is 44. The instantaneous rate of change must also be 44 at least once. Maybe more than once, but at least once. We're guaranteed that according to the mean value theorem, because the mean value theorem says if you find the average rate of change, the instantaneous rate of change will be equal to that at least one time. Well, what does the intermediate value theorem guarantee about the situation? Well, that's connected to the mean as well. So this is the MVT, the IVT. Okay, remember we used the IVT in the past to talk about, well, if I've got a point above the x-axis and a point below the x-axis and they're connected by continuity, I have to cross the x-axis at least once. I can't get around. I can't just skip over the x-axis. It has to be, since it's continuous, I must cross the x-axis. So again, since, the average rate of change is 44, then there exist values both above and below 44. There has to be a value above 44, and there has to be at least a value below 44. That's how you get an average. Sometimes you're faster, sometimes you're slower. Okay, you're never, right on unless you're at constant speed the whole time. But this said our car began and ended at rest. So it can't have been a constant speed the whole time. There had to have been times where the car was faster than 44 meters per second, and there had to have been times when the car was slower than 44 meters per second. Okay, that's our units here. So that would be the argument of the intermediate value theorem. Okay, all right, so you'll have some work on this to do with the two theorems. Most of it will just be using the equations, but sometimes you'll have to apply it to a real situation and figure out, well, what that means since we live in reality. All right, hope you have a good Monday, good start to your week, and some of you I will see in person on Tuesday, and I look forward to that. And the rest, maybe I'll see you on then Thursday, and if you're at home, I'll look forward to seeing you on the screen. All right, see you later.